Welcome to Deep Space Drift. Tonight's journey begins with a question that hides inside the quietest light in the sky. How does a world as calm as the moon begin in fire motion and shattered stone? In the next chapters, the giant impact story unfolds. A glowing debris ring, rock vapor mixing like a thin veil, a newborn moon cooling into layers, chemistry that almost matches Earth, and missing ingredients that quietly escape. Tides that move and orbit outward, and craters that keep time for billions of years. If this kind of slow immersive science feels worth returning to, please like the video and subscribe to Deep Space Drift. It helps this channel keep drifting deeper. Now, let the noise of the day fall away. The moon is already waiting above the dark. A quiet moon hangs in dark space, yet its beginning is loud in physics. The simplest anchor is that a giant impact throws rock into orbit, and that orbiting debris gathers into the moon. In that region, early Earth glows with heat, and a second world approaches on a crossing path. The approach is not a straight line. The motion curves and the closing distance shrinks until gravity steers the final angle. A first payoff arrives in the shape of the event itself. The collision is not a head-on crash. It is a sweeping strike that shears the outer layers and flings a wide spray. A bright arc of molten droplets peels away, and a thin ring-like sheet begins to wrap around Earth. The scene holds a clear physical detail. The spray has a sharp inner edge where tides pull harder, and a softer outer edge where fragments drift. The glow fades outward into a gradient from white-hot near Earth to dull red farther away. The main timescale sits far back in time. The moment happens about 4.5 billion years ago, like the first second of a year-long story. The rest of that year is slow cooling, settling and reshaping. At this distance, the debris does not look like a single object. It looks like a flattened cloud, thicker along the midplane and thinner toward the poles. Each fragment follows an orbit with a slightly different tilt. Many orbits cross so collisions repeat. The second payoff is simple. Repeated collisions do not only break things, they also erase differences in speed, and they coax matter into a shared disk. A calm visual anchor forms of a glowing belt with ripples. The belt carries brighter clumps that trail faint wakes, and darker gaps where fewer fragments pass. The belt is not stable in detail, yet stable in outline. Gravity keeps the overall ring from dispersing at once. Heat keeps much of it soft so contacts can smear and stick. Here, the giant impact idea earns its first strength. It produces an orbiting disk with enough mass and the right kind of material. The moon is rich in rock that matches planetary mantles and poor in iron compared to Earth. A glancing impact naturally favours mantle-rich ejecta. Iron tends to remain deeper, and much of it stays with Earth. A third payoff arrives as a constraint, not a flourish. Any origin story must explain mass orbit and composition at the same time. A co-formed moon would share Earth's iron too easily. A captured moon would arrive with an unrelated chemical signature. The impact pathway threads between these problems by creating new material in a shared neighbourhood. The disk cools unevenly. The inner region remains hotter and more vapour-rich. The outer region cools into droplets and fragments sooner. A thin haze of rock vapour forms above the midplane, and it scatters light into a soft glow. Below that haze, the disk is denser. It casts a faint shadow band where the material blocks its own radiation. The shadow is not sharp like a blade. It is a softened stripe that shifts as the disk thickens and thins. The next visual anchor slows down to a single fragment. A droplet cools from a bright bead into a darker pebble-like shape. It spins as it travels and a glassy skin freezes first. Inside, heat lingers. Over time, many such beads collide, crack and merge. The growth is not steady. It stalls, then surges as local clumps form and sweep up their neighbours. The disk becomes a place of continual small impacts. Those impacts are gentler than the first one, yet they do most of the assembling. The concept that describes this is accretion. Accretion is growth by collisions that add mass. It can be pictured as driftwood gathering in an eddy. It can also be pictured as damp sand forming a larger lump after repeated taps. It matters because it turns a ring into a single moon. The scale shift is quiet but vast. A few hours of orbital motion become thousands of years of repeated sticking. Thousands of years become millions of years of cooling and settling. In that long stretch, the moon begins to separate inside. Dense material tends to sink and lighter material tends to rise. This is not a tidy layering at first. It is a slow sorting in a body that is still warm. A smooth surface appears only after the deeper interior grows more rigid. The disk itself thins as matter leaves it. Some fragments fall back to Earth. Some drift outward and remain. The forming moon sweeps a lane through the disk and the lane becomes wider with time. The next payoff comes as a quiet accounting. The Moon's orbit carries away a portion of the system's spin. The impact can set the combined Earth and debris rotating fast enough to loft material, yet not so fast that everything flies apart. This balance is why the impact is often described as a glancing strike. The angle matters as much as the size. Too direct an ion mixes more than the Moon allows. Too shallow and too little mass enters orbit. The evidence does not rest on a single clue, it rests on several that point in the same direction. One of the most subtle clues lives in isotopes. Isotopes are atoms of one element with different mass. They are like two weights made of the same metal. They share the same shape, yet they tip a scale differently. They matter because their ratios stay recognizable through many physical changes. Minerals lock these ratios into their structure as they crystallize. When lunar and terrestrial rock show very similar isotope ratios for key elements, the simplest reading is shared source material or strong mixing. That similarity is a calm but firm nudge toward an impact that blends mantles. Yet a limit of observation sits here, and it deserves a gentle boundary. No eye witnesses the event. No direct record shows the disk's exact temperature or thickness. The story is inferred from today's orbits from cratered surfaces and from chemical ratios preserved in stones. Models can vary in detail, and different starting angles can lead to similar outcomes. The limit is resolution in time and initial conditions. Tiny changes in impact speed or spin can change the shape of the disk. The uncertainty does not erase the main pattern. It only softens the edges of the reconstruction. Another visual anchor returns to the disk at a later moment. The glow is dimmer now. Clumps are fewer and larger. The midplane is thinner, and the haze above it is fading. A growing moonlet passes through, and its gravity raises a wake like a shallow groove. The groove closes behind it as fragments drift back in. Over many passes, the groove becomes a cleared band. The cleared band is a physical signature of growth. It is an orbiting version of a path pressed through tall grass. The payoff here is a unifying thought. The Moon does not appear as an accident added later. It appears as a product of early planetary crowding and the inevitability of impacts. In that sense, the Moon is a memory of Earth's formation process. It preserves a moment when planets are still half molten and still colliding. The section ends with a soft transition toward deeper structure. The next step is to linger on why impacts happen so often in young systems. Then the view can return to the specific collision that best fits the Moon's quiet chemistry and orbit. The early neighborhood around Earth is quiet in appearance yet restless in motion. The central anchor is that many young bodies share nearby paths, so collisions become likely over long time. At this distance, the Sun's pull shapes broad loops, and each loop is slightly different in tilt and stretch. 2 to 3 concepts guide the section. Orbital crossing sets up repeated close approaches. Gravitational focusing turns a near miss into a hit by bending the path inward. Chaos in many body motion makes long-term prediction blur even when short-term motion feels orderly. A first visual anchor settles into place. A dark plane of space holds many faint ellipses like thin threads laid over one another. Some ellipses touch at narrow junctions called nodes. At each node, speed and direction differ by a little. That little difference is enough to change the next lap. A small payoff arrives with a simple rule. When orbits cross, time becomes a search. Each lap is a new chance for two bodies to reach the same place together. The chance per lap is small. The number of laps is huge. The region looks empty, yet it behaves like a crowded corridor stretched over time. The paths do not need to aim. Repetition supplies the aim. Close approaches begin to matter long before contact. A passing body raises a tide in gravity, not in water. The pull is stronger on the nearer side and weaker on the far side. The result is a brief twist in trajectory. A curve appears in the path shallow at first. In that curve is the second payoff. A near miss does not stay a near miss when gravity has time to act. Gravitational focusing is the quiet mechanism. It makes the target feel larger than its physical surface. A small deflection early becomes a larger deflection later. The path bends like a slow arc in a long throw. In that region, the geometry of an approach matters as much as the size of the bodies. The visual field shifts closer. One object drifts along its ellipse and another arrives on a slightly different ellipse. Their relative motion is not parallel. The distance shrinks. The sky between them seems to thin. The nearer sides brighten from heat stored in rock, and a gentle gradient runs across each surface. The gradient is physical. It marks temperature and glow, not intention. A third payoff arrives at the moment of closest approach. If the pass is distant, the orbits adjust and separate. If the pass is close, the bending becomes decisive. The two bodies fall toward a shared center for a short time. The collision becomes the end of a curve, not the start of a straight line. This is why impacts can be glancing. The approach can arrive with sideways motion already built in. The sideways motion is not an extra feature. It is a natural result of curved orbits and timed encounters. An everyday analogy carries the idea without forcing it. Two marbles roll on a slightly tilted plate. Each marble follows a smooth arc. A small change in speed shifts where the arcs cross. After many passes, a bump becomes likely even if the plate looks wide. The analogy matters because it captures repetition and gentle steering. It avoids the false idea of a single aimed shot. The scale shift deepens. A single orbit around the Sun takes about 1 year, like one page in a very long book. Over about 100 million years, the book gains many millions of pages. Over that many pages, rare events become common. The early inner system contains many leftover bodies. Some are small, some are nearly planetary. The supply of possible impactors lasts until it is depleted by collisions and ejections. A new visual anchor slows down the clock. A broad ring of debris surrounds the Sun. The ring is not smooth. It has thicker bands and thinner gaps. Each band has a soft edge where particles spread out. Each gap has a sharper edge where repeated encounters have cleared material. The boundaries shift and the ring breathes in density. A small payoff is hidden in that pattern. The ring's unevenness shows that gravity sculpts even without collisions. Regions of repeated tugs can herd objects into bands. Other regions can scatter them into gaps. The same shaping can also increase risk near Earth's path. Objects can be nudged into orbit crossing states, then held there long enough for chance to do its work. The motion remains calm to look at and relentless to live through. A subtle limit of intuition appears here. The mind prefers to imagine clean loops that repeat forever. The actual system does not repeat in detail when many bodies interact. Tiny differences in starting position grow. After enough time, two nearly identical simulations diverge. The limit is not a lack of physics. The limit is sensitivity to initial conditions. Another limit is observational. Only the aftermath remains, and that aftermath has been reworked by billions of years. The early population size is inferred, not counted. The mixing and loss of bodies are reconstructed, not watched. This boundary is gentle but real. It keeps the story focused on robust patterns rather than exact timelines. The robust pattern is that crossing orbits and repeated tugs create opportunities for large impacts. The section returns to physical details. An approaching body does not see Earth as a point. It sees a growing disk. That disk has a limb, and the limb is the first place where shadow and light divide. The limb moves across the surface as the rotation turns. The approach angle decides which hemisphere faces the impact corridor. The corridor is not a line. It is a wide tube of possible paths defined by orbital geometry and timing. A new payoff arrives as a calm clarification. Large impacts do not require extreme speeds. They require the right overlap of paths and the patience of time. Even moderate relative motion can deliver enormous energy when masses are large. The energy is set by motion and mass together. The reason the giant impact idea remains plausible is that young systems naturally supply both. The remaining pieces are the specifics, which angles produce the right debris disk, which depths mix and which do not, which parts stay with Earth and which parts reach orbit. The visual field pulls back once more. Faint ellipses cross like a woven lattice. A few crossings are highlighted by brief brightening where close passes stir heat and melt. Most crossings stay dim and nothing happens that day. Over long time, the rare bright events accumulate. The lattice becomes a slow filter that selects one decisive collision out of many near misses. The closing transition stays soft. The next section turns from probability to geometry. It lingers on how a glancing collision can loft mantle rock into a ring and why that ring gathers into one moon. A single collision can look like a flash, yet its most important work is done by geometry. The early anchor is that a glancing impact can lift mantle rock into orbit, which becomes the raw material of a moon. 2 to 3 concepts guide the path. Impact angle controls what gets launched and what stays. Roche limit is the distance where tides can prevent clumping. Debris disk formation turns a spray into a flattened ring that can later accrete. At this distance, Earth is a bright sphere with a molten sheen. Its surface glow has a soft gradient from day side to night side. Another body approaches on a path that curves, and the curve makes the meeting sideways. The first visual anchor is the moment of contact. The incoming body skims the outer layers. A wide crescent of rock is peeled up and out. The edge of that crescent is sharp where the shear is strongest. Behind it, a plume fans outward and thins into a ring. The ring is not uniform. It is thicker near the equatorial plane, and it has a ragged outer boundary where fragments spread. A first payoff arrives in the difference between scraping and drilling. A direct hit pushes material inward, and iron can mix more deeply. A glancing hit shaves the outside, and mantle rock is the easiest to loft. That is why a sideways strike can produce a moon that is rocky and comparatively low in iron. The spray does not travel as a simple cloud. Gravity pulls it into a disk. Each fragment enters an orbit with a slightly different tilt. Those tilts collide and damp out over time. The disk becomes flatter. Heat keeps some of it soft so collisions smear rather than shatter. The ring gains a recognizable inner edge where the pull is strongest. It also gains a faint shadow band where the disk blocks its own glow. The shadow is soft. It slides as the disk breathes in thickness. A second payoff arrives with a boundary that decides when clumps can form. The Roche limit is the distance where tides tear weak clumps apart. It can be imagined as a zone where gravity is pulled in two directions at once. It can also be imagined as a place where a loose snowball would crumble before it hardens. It matters because debris inside that zone stays as a ring while debris outside can gather. The scale shift is quiet and wide. Minutes of impact physics become hours of orbit settling. Hours become years of repeated collisions. Years stretch into thousands and then into millions as the disk cools and the first larger clumps survive. A single number helps hold the distance. The Roche limit for rocky material around Earth is about 3 Earth radii, like placing a small ball 3 arm lengths away from a larger ball. Inside that distance, tides pull too unevenly for fragile piles to stay together. Outside, the tug is gentler and self-gravity can win. The next visual anchor moves outward through the disk. Near Earth, the material is brighter and finer. Farther out, the material is darker and more clumped. The boundary is not a wall. It is a gradient in stability. Small aggregates form, then are pulled apart, then form again. Beyond the critical region, aggregates begin to survive. They orbit like slow-moving islands in a glowing sea. Each island has a leading edge that sweeps up dust. Each has a trailing wake where smaller fragments spiral in. A third payoff arrives as soon as survival becomes possible. The first durable clumps act like nets. They collect far faster than loose dust can. Growth accelerates not because space becomes denser, but because capture becomes efficient. The disk begins to clear a lane. The lane is visible as a darker band that follows the orbit of the growing body. That clearing is the signature of accretion in a ring. An everyday analogy carries the flow without borrowing earlier images. A wet brush dragged through thick paint leaves a trough. Paint flows back slowly, yet the brush passes again and deepens the trough. In the same way, a growing moonlet passes through debris. Debris drifts back, yet repeated passes carve a clearer path. The analogy matters because it captures clearing by repetition rather than by force. A limit of observation enters softly. No direct measurement records the impact angle, the exact speed, or the disk's initial temperature. The limit is inference from survivors and models. Modern rocks preserve composition, not the original disk thickness. Orbital parameters preserve the end result, not every step. Simulations can recreate a plausible disk, yet small changes in starting spin can change details. The uncertainty lives in those details. The broad outcome remains stable across many plausible inputs. A rocky disk forms most naturally from a glancing strike. The section returns to physical texture. In the disk, fragments collide at different speeds. Some collisions melt surfaces into smooth skins. Some collisions chip edges into angular shapes. The result is a mixture of rounded beads and jagged shards. Light scatters differently from each. A soft haze forms above the disk as hot vapor rises, then cools and condenses. The haze is thin, yet it can blur the sharpness of the inner ring when seen from afar. A payoff arrives in the disk's cooling rhythm. Cooling is not only loss of heat. Cooling is a change in behavior. When the material is too hot, it flows and resists stable clumping. When it cools enough, collisions can build rather than smear. That transition is one of the quiet hinges of lunar origin. The growing body outside the Roche limit begins to dominate its neighborhood. Its gravity pulls in fragments from slightly different paths. The disk becomes patchier. Bright clumps appear where many pieces share a track. Dark gaps widen where those pieces have been collected or have fallen back to Earth. The view pulls back to show the full ring around the planet. The ring is slightly tilted at first, then slowly flattens as collisions damp motion. The ring's outer edge becomes smoother. The inner edge remains sharper because tides keep it constrained. The closing transition stays gentle. The next section turns from geometry to assembly. It follows how countless small collisions turn a ring of debris into one coherent moon, and how heat and sorting begin inside that new body. A ring of debris can seem like a scattered aftermath, yet it carries a quiet order. The early anchor is that repeated collisions inside the disk turn many fragments into one growing moon beyond the tidal boundary. 2 to 3 concepts guide this section. Accretion builds mass through sticking collisions. Collisional damping reduces random motion and flattens the disk. Angular momentum is the stored spin and orbital motion that must be shared, not destroyed. At this distance, the disk is a thin band around Earth. It has a brighter inner rim and a dimmer outer rim. The brightness fades outward in a gentle gradient as temperature drops. The band casts a soft curved shadow on itself where it is thickest. The first visual anchor is a slow drift through that band. Small fragments move on slightly different tracks. Their paths cross like threads in a loom. Each crossing is a chance for contact. Many contacts are light taps. Some are faster strikes that shatter edges. A first payoff arrives in what collisions really do here. Collisions do not only break, they also trade energy away as heat and deformation. That trade makes orbits less wild. The disk becomes calmer in motion even as it stays busy in impacts. The flattening begins in a simple way. Pieces on tilted orbits collide more often because their paths cut through the dense midplane. Those collisions reduce tilt. Over time, more mass stays near one plane. The disk's thickness shrinks. Its edge becomes sharper. The ring starts to look less like a cloud and more like a banded structure with a defined boundary. In that region, there is a delicate division. Inside the tidal boundary, clumps are pulled apart before they can strengthen. Outside it, clumps survive long enough to grow. The next visual anchor forms right near that division. A stream of fragments crosses outward and begins to linger. The stream is brighter at first, then it breaks into a chain of knots. Each knot is a temporary pile. Some piles stretch into elongated shapes as tides pull unevenly. Some piles hold together and round off. The rounding happens because loose pieces settle into a smoother form when motion slows. A second payoff arrives with the first durable knot. Once one knot survives, it becomes a collector. It sweeps a wider area than its size suggests because gravity draws in nearby fragments. The collector leaves a wake, a subtle trough in the density of the ring. The trough is a physical feature. It is darker not because it is colder, but because material has been removed. Each orbit deepens that trough. The collector grows, then begins to clear a lane. The lane is not empty, it is simply thinner than the surrounding band. An everyday analogy holds the growth pattern without repeating earlier images. A crumb rolling across a sticky tabletop gathers more crumbs. The first crumb is small and easy to ignore. After many passes, it becomes a rough ball with a wider sweep. The analogy matters because it captures runaway capture in a gentle way. Growth accelerates not through intention, but through increased reach. The disk's angular momentum sets the pace and the shape of growth. Angular momentum is motion that resists being stopped. A spinning skater keeps spinning without an outside push. A spinning top keeps its axis stable until friction slowly changes it. It matters because the disk cannot simply fall straight in. It must redistribute motion while it gathers. When fragments collide, some angular momentum is moved outward and some inward. The outer region can gain a little distance while the inner region can lose it. This exchange helps push more material beyond the tidal boundary where clumps can survive. A scale shift arrives in a calm step. A single collision lasts seconds. A single orbit takes hours. Thousands of orbits stretch into many years. Over about 1,000 years, like counting slowly through a long winter, the disk can build a dominant moonlet and clear much of its lane. The number is order of magnitude safe, and it points to patience in physics. In that time, the disk changes texture. Early on it is grainy and bright. Later it is patchy with clear clumps and clear gaps. The surface of the growing body remains hot. It glows with a subdued red and shows a smooth sheen where melt pools. Around it, smaller fragments trace curved arcs, and each arc is a record of capture. A third payoff arrives as the reason one moon forms instead of many. When one body becomes large enough, it stirs the remaining debris. It increases relative speeds for smaller clumps. Faster impacts tend to break those clumps apart before they can compete. The largest body wins by making the environment harsher for rivals. The process is calm in outcome. It is simply selective in mechanics. A limit of observation belongs here as well. The disk no longer exists to be measured directly. Its density and temperature are reconstructed from models and from the moon's final orbit and composition. The limit is that many different initial disks can produce a similar moon. The models depend on assumptions about melt behavior, fragment size, and how heat is lost. There is also a limit in preserved evidence. Later impacts and internal cooling erase some of the earliest textures. The broad behavior remains. Collisions damp motion. Surviving clumps grow fastest. One body becomes dominant beyond the tidal boundary. The visual field returns to the ring for a final slow pass. The inner edge stays sharp because tides keep it constrained. The outer edge is softer because material can spread. The cleared lane around the growing moonlet becomes wider. The lane has a faint boundary line where density rises again. Light scatters differently across that line, making it look like a subtle seam in the disk. The moonlet's orbit becomes smoother as random kicks fade. Its shape rounds, Its surface remains hot enough to flow in places. The section ends with a gentle turn inward. Once a single body forms its own heat becomes the next story. The next section follows how a global melt layer settles into layers and how that settling begins to shape the moon's crust and interior. The newborn moon cools in silence, yet its interior keeps moving for a long time. The early anchor is that a global magma ocean cools and separates into layers which builds the first crust. 2 to 3 concepts guide the section. Magma ocean is a deep global layer of melt. Fractional crystallization is separation as minerals freeze at different times. Differentiation is the overall sorting into layers by density. At this distance, the young moon is a dim red sphere. Its surface is not solid rock. It is a skin that wrinkles and smooths as melt rises and sinks beneath it. A faint sheen runs across the limb where light grazes the curved edge. That limb is a physical boundary. It marks where glow turns to darkness in a narrow band. The first visual anchor settles on a slow close view of the surface. Dark rafts drift over a brighter melt beneath. The rafts are irregular. Their edges curl and break, then fuse again. Between them, thin channels of glowing melt form branching lines. A first payoff arrives in why a magma ocean forms at all. The moon is built from energetic collisions and hot debris. That assembly stores heat deep inside. The result is a body that can melt on a global scale rather than in scattered pockets. The molten state is not an extra detail. It is the starting condition that makes later chemistry readable. Magma ocean is a global layer of molten rock. It is like a deep pot of thick liquid that cools from the top. It is also like a pond that freezes on the surface first while the interior stays fluid. It matters because it allows minerals to separate cleanly as they crystallize. Cooling begins at the surface, yet the interior does not freeze evenly. Dense minerals can form and sink. Lighter minerals can form and float. The floating matters because it builds a crust. The sinking matters because it shapes the mantle beneath. The next visual anchor moves into the interior without breaking calm. A cross-section appears as a gradient of brightness. Near the surface, the melt is cooler and more viscous. Deeper down, it is hotter and smoother. Within the melt, crystals appear like pale specks. They drift. Some specks gather into darker streaks that fall. Others gather into lighter streaks that rise. The rising streaks collect beneath the surface skin and spread sideways. A second payoff arrives in the direction of sorting. Sorting is not a choice. It is a consequence of density. Heavy crystals settle like grains in thick syrup. Light crystals rise like froth in a slow boil. When enough light crystals accumulate, they create a coherent layer. That layer insulates the melt below. It changes the cooling rate and the pattern of later crystallization. This is fractional crystallization in a calm form. Fractional crystallization is minerals freezing at different times and separating. It can be pictured as a jar of mixed particles where the heaviest settle first. It can also be pictured as a tray of waxes that harden in stages, each stage forming a distinct layer. It matters because it produces a crust with a different composition than the deeper interior. One number helps hold the timescale of this slow sorting. The magma ocean can cool and largely crystallize over about 100 million years, like letting a thick stew cool so long that the surface forms a stable skin and the interior gradually firms. The comparison is gentle, and it keeps the scale grounded. The scale shift is wide and quiet. A droplet cools in seconds. A surface raft stiffens in hours. A global interior cools over millions of years. Over that span, the moon changes from a glowing sphere to a darker body with a rigid shell. Physical details mark that change. The crust grows thicker and more continuous. Its underside remains warm and slightly ductile for a long time. A gradient in temperature persists from the surface down. That gradient drives slow motion even when the surface looks still. The next visual anchor returns to the surface as it becomes more solid. The glow fades from red to dark grey. Bright patches appear where fresh crust is thinner and warmer below. Those patches have soft edges that blend into darker surroundings. In low places, melt can still pool and then freeze, leaving smooth, glassy plains. Along the limb, the new crust casts a subtle shadow line, where small topographic steps break the smooth curve. A third payoff arrives in why the moon's crust is not a random skin. It is a record of flotation. When lighter minerals float and freeze, they create a crust that can be thicker than expected for a small body. That flotation crust also traps chemical differences. It preserves a signature that later impacts cannot fully erase. This is why lunar samples often carry clues about early sorting rather than only about later cratering. A limit of observation sits calmly in the middle of this story. The interior cannot be seen directly. Its early layers are inferred from surface rocks and from how the moon responds to gravity and rotation over time. The limit is resolution and access. Later impacts excavate some depth, yet they mix material and reset textures. Later cooling can also alter minerals. Models of crystallization depend on assumptions about melt composition and how efficiently crystals separate. The broad pattern remains robust. A global melt separates into layers, and the crust forms by flotation of lighter minerals. The section returns to a physical boundary that matters. The growing crust is a lid. Beneath it, heat must escape through conduction and occasional cracking. The lid can thicken unevenly. Where it is thicker, the surface cools faster and becomes darker. Where it is thinner, the surface stays warmer and can sag slightly, leaving gentle basins. Those basins are not yet the familiar large craters. They are early shape changes from cooling and settling. An everyday analogy carries the lid behavior without repeating earlier images. A cooling layer of pudding forms a skin. The skin can wrinkle when the interior shifts. It can also break and heal as warmer material rises. The analogy matters because it captures a calm surface hiding motion beneath. Another payoff arrives as the moon's future is set by this early lid. A thickening crust reduces later volcanism by making melt harder to reach the surface. It also preserves early chemical patterns by sealing them in. The moon becomes a body with an ancient surface and a slowly quieting interior. The closing transition stays soft and forward. The next section follows chemical fingerprints more closely. It lingers on isotopes and mixing, and on why Earth and Moon can look so similar in some measures, while still showing meaningful differences. A tiny difference in atoms can guide a story that spans the age of worlds. The early anchor is that isotope ratios link Earth and Moon materials so closely that strong mixing is hard to avoid. 2 to 3 concepts carry the section. Isotopes are atoms of one element with different mass. Isotope ratios are the relative abundance of those masses. Mixing is the blending of reservoirs during and after the impact. At this distance, the moon's surface is quiet and dark, yet its rocks carry internal patterns frozen into crystal lattices. Along a broken cliff face, fresh rock shows pale and dark bands. The bands are not paint. They are layers of minerals that cooled at different times. Each layer has a slightly different density and grain size. Light behaves as a soft scatter across the fine grains and a sharper glint across the coarse grains. The first visual anchor is a slow drift through a cooling melt. Tiny crystals appear as bright flecks. They settle and turn. Some collect into thin ribbons that sink. Some collect into buoyant patches that rise. Within each crystal, atoms fit into repeating positions like a calm geometric wallpaper. That repeating pattern is where isotopic information can be held steady through time. A first payoff arrives as soon as the word isotope becomes plain. Isotopes are not different elements. They are the same element with a heavier or lighter version. They behave almost the same in chemistry, yet not perfectly the same. This small mismatch shows up in how materials form and separate. The mismatch is subtle, yet it is measurable in principle. A second payoff arrives in what a ratio can do that a single measurement cannot. A ratio compares one isotope to another in the same sample. That comparison cancels many sources of noise. It becomes a stable reference that can travel through melting, crystallizing, and grinding. In that sense, a ratio is a pattern more than a quantity. It is a pattern that can be compared across rocks from different places. In that region, the giant impact idea faces a calm test. If the moon forms mostly from an incoming body, then many isotope ratios might differ from Earth. If the moon forms mostly from Earth's mantle, then the ratios might match too well. The surprise is how close many of these ratios appear between Earth and Moon for key elements. That closeness is not a single point. It is a consistent theme across several systems. The simplest way to make two reservoirs so similar is to mix them strongly while everything is hot and mobile. The next visual anchor turns back to the impact aftermath without showing the impact itself. A thick disk of glowing material circles Earth. Above the disk is a thinner veil of vapor. The veil is brighter near the inner edge and dimmer outward. It has a soft boundary, where turbulence fades into stillness. Within the veil, eddies twist and unwind. The twisting is not violent in appearance. It is steady folding in a hot, low-density medium. A small payoff arrives with the role of vapor. When rock becomes vapor, it can mix far more efficiently than solid fragments can. Vapors can blend at the scale of the whole disk. They can exchange atoms between droplets and the surrounding gas. Over time, that exchange can erase differences that would remain locked in solid chunks. The disk does not need to be perfectly uniform. It only needs enough repeated contact for materials to share a common reservoir. The third payoff arrives with a quiet clarification. Similar isotopes do not prove a single exact impact scenario. They narrow the space of scenarios. They favor outcomes where Earth's mantle material and the impactor's mantle material become deeply intertwined. They also favor scenarios where the disk remains hot long enough for exchange to matter. This is why many models focus on mixing in the post-impact disk as much as on the impact itself. An everyday analogy can hold the idea without leaning on human intent. Two warm currents meet in a shallow sea. One current carries slightly heavier grains, the other carries slightly lighter grains. As the currents swirl back and forth, grains are lifted, dropped, and lifted again. After enough cycles, the shoreline sand no longer shows a clean boundary. It shows a blended gradient where the origin is hard to separate. The analogy matters because it captures repeated exchange rather than one-time blending. It also keeps the focus on motion and contact, not on labels. One number helps ground how subtle these differences can be. Some isotope differences are as small as 1 in 10,000, like 1 grain of salt lost in a large bowl of rice. That scale of difference demands patience and caution. It also hints at why similarity is so striking. When differences can be that small, a strong mixing process can easily smooth them away. Yet some differences should remain if two sources stay separate. The closeness suggests separation does not last. The scale shift arrives gently. At the atomic scale, isotopes differ by a few neutrons in a nucleus. At the crystal scale, those atoms sit in repeating lattices. At the planetary scale, reservoirs of melt and vapor exchange material across thousands of kilometers. Seconds of turbulence in hot vapor can influence millions of years of cooling that follow. A new visual anchor returns to the moon's forming crust. A thin flotation crust grows above the magma ocean. Beneath it, melt moves slowly. Crystals settle in faint streaks that arc like long commas. The streaks are denser toward the center and thinner toward the edges. A shadow line marks where the crust is thick enough to block the glow from below. That shadow line creeps outward over time as the crust thickens. A payoff arrives in how this later cooling can preserve the earlier mixing. Once minerals crystallize and lock in ratios later, heating must be strong to reset them. Many processes later on are too gentle to erase the signature completely. Impacts can melt local regions, yet they do not always homogenize the entire body. This is why early mixing can remain readable long after the disk is gone. A limit of observation belongs here, and it is specific. Isotope measurements depend on sample representativeness and analytical precision. Only a small fraction of lunar materials are available for detailed study. Many samples come from limited terrains. Later impacts can mix surface layers, which blurs local context. Some isotopic systems are more sensitive than others, and some are harder to measure cleanly. Models must also choose how efficiently vapor and melt exchange atoms. That efficiency is not directly observed in an ancient disk. It is inferred from physics and from outcomes. The limit is not that the method is weak. The limit is that the early environment cannot be revisited to test each assumption directly. Even with that boundary, the broad conclusion remains stable. Many key isotopic similarities point toward extensive post-impact mixing. That mixing helps explain why the moon looks so Earth-like in several chemical fingerprints. At the same time, the moon is not a perfect copy. Differences in other properties still appear, especially in materials that are easily lost as vapor during high heat. The closing transition stays soft and forward. The next section follows the puzzle that grows out of this similarity. It lingers on how mixing can be so effective in some measures, while other differences remain as quiet evidence of loss and fractionation. The moon can match Earth in quiet chemical fingerprints and still feel strangely missing in others. The early anchor is that volatile loss during the hot disk phase leaves the moon drier even when many isotope ratios remain similar. 2 to 3 concepts guide this section. Volatiles are materials that evaporate easily when heated. Evaporation is the escape of atoms from hot surfaces into gas. Fractionation is a small shift in composition caused by selective loss. At this distance, the post-impact disk is no longer a bright explosion. It is a broad glowing band with a thin veil above it. The veil is brighter near the inner rim where heat is strongest. It fades outward into a dim gradient where cooler droplets dominate. The first visual anchor is a slow look at the disk surface. Droplets rise and fall through a warm gas like beads in thick steam. Their outer skins glint then dull as they spin and cool. Between them, vapor forms faint streaks that curl into eddies. The eddies have soft edges. They twist without sharp borders, and they carry material from one region to another. A first payoff arrives in a simple reason for dryness. When everything is hot, the easiest things to lose are the easiest things to evaporate. The disk is not sealed. It has an upper surface where gas can expand into surrounding space. From that surface, lighter and more volatile components can escape more readily than heavier and less volatile ones. The loss does not need to be complete. Even modest loss changes what remains because the starting inventory is limited. Volatiles are materials that evaporate at relatively low temperatures. They behave like scent rising from warm tea. They also behave like dew disappearing after sunrise. They matter because they carry water and other easily moved components that influence later geology. The Moon's relative lack of some volatiles suggests that its building material spends time in conditions that allow escape. The next visual anchor shifts to the disk's upper veil. A thin layer of vapor sits above the denser midplane. Within it there are brighter filaments where gas is hotter and more concentrated. There are darker patches where the gas is thinner. At the boundary between veil and space, the gas becomes so rare that collisions are less frequent. That boundary is not visible like a wall. It is a fading edge where the veil becomes transparent. A second payoff arrives with the role of the boundary itself. Escape is easiest where collisions are rare. In a dense, gas atoms bounce and return. In a thin, gas atoms can travel farther without being turned back. The disk naturally creates both regimes. Near the midplane, mixing is strong. Near the top, the path outward is clearer. This is how the same environment can mix isotopes efficiently and still lose volatiles. Mixing works best where material stays in contact. Loss happens where material can leave. The two processes can run together without cancelling each other. An everyday analogy carries the idea without repeating earlier images. A warm loaf cools on a rack. Inside, heat stays and flavours mingle. At the surface, aroma escapes into the room. The loaf remains one loaf, yet it becomes less fragrant at the surface over time. The analogy matters because it separates internal blending from surface loss. It also keeps the focus on gradients and boundaries. One number helps ground the idea of heat without turning into a formula. Temperatures in parts of the disk can exceed 2000 degrees, like the heat near the heart of a kiln. At such heat, many rocky components can exist partly as vapor. In that state, the difference between staying and leaving becomes a matter of pressure and height above the midplane. A gentle scale shift arrives. The difference begins at the scale of single molecules. It becomes measurable in the bulk chemistry of crystals. Over millions of years, it influences how much melt can later rise and erupt. Over billions of years, it influences how long the interior can stay active. A third payoff arrives as a quiet clarification about fractionation. Fractionation is not a dramatic separation into pure substances. It is a bias. It means one component is lost slightly more than another. Over time, repeated loss from a hot surface can create a measurable shift. The Moon's pattern of being depleted in some volatile elements fits this kind of biased loss. It also fits loss during cooling of a hot disk and a hot-forming moon. The physical details remain steady. The disk has a hot inner zone that glows brighter. It has a cooler outer zone that clumps. The vapor veil has a top edge where density falls. The forming moon has a surface that cools into a skin. That skin can trap some material beneath while allowing other material to escape earlier. The scene moves to a cooling droplet at the edge of the disk. The droplet spins slowly. Its outer layer cools first and becomes glassy. From that glassy surface, the most easily evaporated components leave first when the surface reheats during a collision. The droplet is struck again by another fragment. The impact briefly reheats the surface and renews evaporation. Over many such events, the droplet becomes subtly changed. The next visual anchor returns to the forming moon's surface. The young crust is thin and fractured. Warm melt glows through narrow cracks like faint lines on dark stone. Near each crack there is a small gradient in colour, brighter near the opening, darker a short distance away. That gradient marks heat and cooling. It also marks where gases can vent most easily. A payoff arrives in why dryness can persist. Once volatiles are lost early, they are hard to regain. There is no simple reservoir in the environment that refills them. Later impacts can add some material, yet the dominant chemical character is set during formation. The Moon begins on the drier side, and later evolution unfolds from that starting point. A limit of observation is needed and specific. Volatile histories are difficult to reconstruct because volatiles move easily and can be lost or added later. Surface materials can be altered by later heating, and impacts can both remove and deliver volatiles. Measurements may sample rocks that have been heated or mixed long after formation. Models must estimate how long the disk stays hot and how thick the vapor veil is. Those parameters are inferred rather than directly observed. The limit is not that volatility is unknowable. The limit is separating early loss from later overprinting with high confidence. Even with that boundary, the overall pattern stays coherent. A hot mixing disk can also be an evaporating disk. Similarities in many isotopes point to shared reservoirs. Depletions in some volatiles point to open boundaries and selective escape. The closing transition stays calm. The next section turns from what is missing to what is sorted. It follows how the Moon's interior layering and crustal chemistry preserve the results of early melting, mixing and loss. The Moon's surface looks simple at a glance, yet its colours hint at a layered interior. The early anchor is that early melting and sorting create distinct layers, and later eruptions and impacts reveal parts of that hidden structure. 2 to 3 concepts guide the section. Differentiation is the sorting of materials into layers by density. Incompatible elements are atoms that stay in melt instead of entering early crystals. Buoyancy is the tendency of lighter material to rise and form a crust. At this distance, the Moon is a quiet sphere with bright highlands and darker low plains. The boundary between them is rarely smooth. It is scalloped. It bends around basins and ridges like a coastline seen from far above. The first visual anchor is a slow pass over a bright upland. The ground is pale and finely broken. Small craters overlap like shallow bowls. Their rims cast soft shadows that shift with the low sun angle. In the deepest crater walls, thin bands of lighter and darker material appear, stacked like pages exposed at the edge of a book. A first payoff arrives in why bright highlands form at all. When a global melt cools, some minerals float because they are less dense. Those floating minerals can gather into a crust. The crust becomes brighter because its minerals reflect more light than darker basaltic rocks. The brightness is not paint. It is the optical effect of composition and grain texture. The highlands are a surface expression of flotation. A second payoff arrives in how the interior keeps a chemical memory. As early crystals form, many trace elements refuse to enter them. They remain in the melt. Over time, the remaining melt becomes enriched in these incompatible elements. The enrichment is quiet. It does not require large amounts of material. It only requires repeated removal of early crystals that take other elements away. This late melt is chemically distinct. It can later feed unusual volcanism or create localized layers beneath the crust. The next visual anchor moves inward as if the Moon is sliced in half. Near the top is a pale crust. Beneath it lies a darker mantle. Deeper still is a region that is hotter and more uniform. Between crust and mantle, a boundary appears as a thin, uneven interface. It is not a perfect sphere. It rises and falls like a slow wave. Where the crust is thicker, the boundary dips downward. Where the crust is thinner, the boundary arches upward. A third payoff arrives in the usefulness of that boundary. A layered body responds differently to stress and heat than an unmixed one. Layers guide how melt moves. Layers guide where fractures may open. Layers also guide what an impact can excavate. When a large crater forms, it can expose deeper material at the center. That material can differ from the rim material, and the contrast can be seen as a color change or a change in reflectivity. In that region, buoyancy continues to matter long after the first crust forms. The crust is light and it tends to stay on top. The mantle beneath can still creep slowly when warm. Over long time, this creep can relax sharp topography. It can soften basin edges. It can also allow denser material to settle. The surface does not need to move fast for interior motion to matter. The scale shift is gentle and wide. A crystal grows in moments. A layer forms over thousands of years. A crust and mantle mature over millions. Over billions of years, impacts and eruptions reveal the results in scattered patches. One number helps anchor the thickness of the early crust. The lunar crust can be about 50 kilometers thick on average, like the rind on a large melon compared to its full diameter. The comparison stays simple. It shows that the crust is thin relative to the whole Moon, yet thick enough to shape what reaches the surface. The next visual anchor shifts to a boundary between bright and dark terrain. The edge is not a straight line. It is a broad zone where bright fragments are mixed into dark plains. The zone looks like a gradient. Small bright blocks lie embedded in darker material like islands in a calm sea. Some blocks cast crisp shadows, which implies they are fresh and steep. Others are softened, which implies they have been worn by countless tiny impacts. A payoff arrives in why dark plains appear smoother. Dark plains are often made of later lavas that flood low basins. These lavas come from partial melting in the mantle. Partial melting means only a fraction of rock melts, and that melt rises. The melt is denser than the floating crust minerals, yet it is buoyant compared to the surrounding solid mantle. It finds pathways upward through cracks and weak zones. When it reaches the surface, it spreads and cools into broad sheets. The sheets fill low areas and bury older craters. The darkness is a compositional signature of iron-rich silicates, not an effect of lighting alone. The story returns to incompatible elements without using dense lists. Late-stage melts enriched in incompatible elements can form concentrated zones beneath the crust. These zones are chemically fertile. They can melt at slightly lower temperatures than surrounding mantle. They can act like a reservoir that feeds later activity in specific regions. An everyday analogy holds the enrichment without repeating earlier ones. When soup simmers, slowly heavier ingredients settle and lighter oils rise. Spices that dissolve remain in the broth. As liquid reduces, the broth becomes more strongly flavored even if nothing new is added. The analogy matters because it captures concentration by removal and reduction. It also stays tied to physical separation in a warm fluid. A limit of observation belongs here, and it is specific. The deep interior layers cannot be seen directly. Only indirect clues exist. A signal would travel through the moon differently if it meets a sharp boundary. Gravity would vary slightly if dense regions lie closer to the surface, yet these clues are blurred by later impacts and by the uneven crust. The limit is resolution and uniqueness. Different interior structures can produce similar surface patterns. Different histories can also produce similar cratered terrain. This is why models of lunar layering often focus on broad constraints rather than exact maps. The visual field slows again over an ancient basin rim. The rim is bright and rough. It is made of excavated crustal material. Inside the basin, the floor is darker and smoother. Near the basin center, a low-rise stands like a dome. Its slopes show mixed tones. The dome hints at uplift of deeper material during the impact. The contrast between rim and floor is a visible sign of depth. A payoff arrives in how impact and volcanism cooperate to reveal layers. An impact excavates and fractures. Fractures create pathways. Later melt can use those pathways. When lava floods a basin, it is not only filling a hole, it is sampling the interior. The chemistry of that lava and the minerals it carries can carry information about mantle source regions. The section ends with a gentle transition toward motion in orbit. Once layers and crust are established, the Moon and Earth begin a long exchange of tidal energy. The next section follows how tides reshape distance and rotation over immense time without needing dramatic events. A slow pull can reshape a whole orbit without leaving a single scar. The early anchor is that tides transfer rotational energy into orbital motion, so the Moon drifts outward while Earth's spin slows. 2 to 3 concepts guide the section. Tidal bulge is a slight stretching caused by gravity. Tidal torque is the twist that transfers energy and angular momentum. Tidal locking is the state where one side keeps facing the other due to long-term torques. At this distance, Earth is a bright sphere with a faintly raised pair of bulges along the line to the Moon. The bulges are not mountains. They are broad swellings in the shape of the planet. Their edges are gentle and their crests are wide. The first visual anchor is a calm view of those bulges from above the equator. As Earth rotates, the bulges do not stay exactly aligned. They lag or lead slightly, because material resists instant change. The lag is a physical detail. It is a small angle between the line to the Moon and the crest of the bulge. That small angle is where the long-term change begins. A first payoff arrives in the direction of the push. When a bulge is offset, its gravity pulls on the Moon in a way that is not purely inward. It adds a slight forward tug along the Moon's path. A forward tug increases orbital energy. The orbit grows. The Moon slowly recedes. The same interaction applies an opposite twist to Earth. Earth's rotation loses energy and slows. Nothing dramatic is needed. A steady small torque working over long time is enough. The scene shifts to the Moon's own shape under the same forces. The Moon is stretched slightly as well. Its near side and far side differ by a tiny amount in gravitational pull. The Moon's body is not perfectly rigid early on. Warm interior layers can deform and then relax. Each deformation dissipates energy as heat. That dissipation matters because it damps wobble and helps the Moon settle into a stable rotational state. A second payoff arrives in why one face comes to dominate. Tidal locking is a long-term outcome of repeated deformation and energy loss. It is not a snap into place. It is a gradual reduction of relative spin until the Moon rotates once per orbit. When that happens, the same hemisphere remains oriented toward Earth. The boundary between light and shadow on the Moon's limb becomes repeatable from orbit to orbit. The Moon's nights and days become linked to its orbital period rather than to a separate spin. The next visual anchor widens into a view of 2 spheres and their connecting line. Along that line, the bulges on Earth are visible as a subtle elongation. The ocean-like swell is higher on the side closer to the Moon, and also on the far side. Between those crests are lower belts. The belts circle the planet and create a slow gradient in height. As Earth spins, the gradient travels around the globe, yet the bulges try to follow the Moon. The mismatch creates friction and internal flexing. The friction is invisible in space, yet it is the engine of change. A third payoff arrives as a quiet conservation story. Angular momentum is not lost, it is exchanged. Earth gives up some spin. The Moon gains some orbital motion. The system shifts its balance while keeping the overall accounting consistent. This is why the Moon can move outward while Earth's day lengthens. The change does not require an external push. It is an internal redistribution driven by gravity and delayed response. An everyday analogy carries the mechanism without repeating earlier images. A heavy rug is pulled gently across a wooden floor. The rug does not move as a rigid sheet. It stretches and bunches. The bunch travels and friction heats the fibers. Over time, a steady pull can move the rug far. The analogy matters because it shows how slow deformation plus friction can produce long-distance change. It also captures the idea of a lagging bulge that transfers force. One number anchors the modern scale of the outcome. The Moon is about 380,000 kilometers from Earth today, like placing a small ball across a long city-to-city distance. The number is round enough to keep speech clean. It also suggests how far the orbit has grown compared to the early state when the Moon is much closer and tides are stronger. The scale shift is gentle and wide. In a single hour, the bulge moves a little as Earth turns. In a single year, the Moon completes many orbits. Over millions of years, small changes in distance accumulate. Over billions of years, the orbit transforms from a close companion to a far one. The strength of tides falls with distance. The torque weakens. The outward drift slows. The process is self-moderating. It is strongest when the Moon is close and weaker as the Moon recedes. The next visual anchor focuses on the Moon's near side as seen from far away. The same face is presented again and again. The terminator line between day and night slides, yet the broad pattern of dark plains and bright highlands remains in the same orientation. This stability is a surface hint of tidal locking. On the far side, the pattern is different, yet it is hidden from direct alignment. The fixed presentation is not a mystery. It is a dynamical endpoint. A payoff arrives in how tides can also influence internal heat early on. When the Moon is closer, flexing is stronger. Flexing generates heat. That heat can help maintain partial melt in the interior for longer. It can influence when volcanism wanes. It can also affect how quickly the interior becomes rigid. The same tidal system that changes the orbit can quietly shape the thermal history. A limit of observation is needed and specific. The exact early distance of the Moon is not measured directly. It is inferred from models and from clues preserved in rocks. The ancient record of tides is incomplete because surfaces are reworked. Even when some geological indicators exist, they may not capture global behavior. The efficiency of tidal dissipation depends on interior structure and ocean distribution on Earth. Those change over time. The limit is that many different dissipation histories can lead to the same present distance. This is why reconstructions focus on ranges rather than a single precise curve. Even with that limit, the direction of change is robust. Tides move energy from spin to orbit. The Moon recedes over time. Earth's rotation slows. The rate varies, yet the trend persists. The section returns to physical details at the interface of gravity and shape. The bulge is not a point. It has a broad crest and a gentle slope. Its crest is offset. That offset is the source of torque. The offset itself depends on how quickly material responds. A more fluid body aligns more quickly and dissipates differently. A more rigid body holds the lag and dissipates differently. The system's evolution depends on these properties. The closing transition stays soft and forward. The next section follows what the changing orbit means for the Moon's surface record. It lingers on craters and basins as timestamps, and on why an airless world keeps old scars so faithfully. A crater is a moment that refuses to fade because the Moon has little to erase it. The early anchor is that an airless surface preserves impact scars for billions of years, turning craters into a timeline. 2 to 3 concepts guide the section. Impact cratering shapes basins and ejecta patterns. Regolith is a blanket of broken rock made by repeated impacts. Space weathering is slow alteration by tiny particles that darken and soften contrasts. At this distance, the lunar surface is a field of overlapping circles. Some circles are sharp and bright, some are softened and dark. Each circle has a rim that rises and then drops into a bowl. The rim casts a narrow shadow line when the sun is low. The shadow line is a physical detail that reveals slope and height. The first visual anchor is a fresh crater seen at dawn. Its rim is bright and crisp. The interior wall is steep and it shows faint terraces like steps carved into rock. At the center, a small peak rises. The peak is not a mountain grown by uplift. It is a rebound of material that springs upward after the shock. Around the crater, pale rays extend outward. They are thin streaks of brighter debris. They cross older terrain in long lines that look like threads laid on dark cloth. A first payoff arrives in why rays look bright. Freshly excavated material has not been darkened by long exposure. It reflects more light because its grains are sharper and less coated. Over time, that brightness fades as the surface is altered. This makes rays a gentle clock. Bright rays imply youth. Faint rays imply age. The Moon does not need rivers or wind to keep time. It uses gradual darkening and the stacking of craters on craters. Regolith is a blanket of crushed rock and dust. It behaves like dry flour spread over stone. It also behaves like snow that never melts but is constantly churned. It matters because it records constant small impacts and it buries older surfaces. Every small impact breaks rock into smaller pieces. Every piece becomes part of the blanket. The blanket thickens with time and it softens the sharpness of older features, yet it does not erase them completely. It preserves outlines as muted relief. The next visual anchor shifts to an ancient basin. The basin is vast and shallow. Its rim is broken in segments. Inside the basin, the floor is smoother than the surrounding highlands. A ring of low hills circles the interior like a faint ripple frozen in stone. Along the rim, shadows gather in long arcs. Those arcs show that the rim is still elevated despite immense age. A second payoff arrives in how basins form and why they last. A large impact excavates deep material and throws it outward. The thrown debris forms a thick ejector blanket near the rim and a thinner blanket farther away. The blanket is not even. It has lobes and scalloped edges where debris lands in surges. The basin's shape is then modified by collapse and uplift, yet its fundamental circle remains. On a world with air and water, such shapes are softened quickly. On the moon they persist. The surface becomes a palimpsest, yet the ink is never fully wiped. Space weathering changes the surface quietly. Tiny impacts from micrometeoroids melt the outermost grains. Particles from the sun can implant and alter the chemistry of those grains. The result is a thin coating that darkens the soil. It also reduces contrast between different rock types. This is why old highlands and old lavas can both look muted. The third payoff arrives in the contrast between small impacts and big ones. Big impacts carve the obvious circles and basins. Small impacts do the long-term maintenance of the record. They grind, they mix, they build the regolith. They also create the texture that holds light differently from one patch to the next. Over time, a surface becomes darker and more uniform, yet the geometry of craters remains as a persistent map. The scale shift is gentle and wide. A single impact lasts seconds. Ejecta settles in minutes. The crater cools in days. The ray system can remain bright for millions of years. The basin outline can remain visible for billions of years. One number anchors this long persistence. Some of the oldest large lunar surfaces are about 4 billion years old, like a page kept from the earliest chapters of a long book. The number is broad and safe. It reminds that the record reaches back near the early inner system. An everyday analogy carries the stacking of craters without repeating earlier ones. Footprints pressed into dry clay can remain if nothing washes them away. New footprints can overlap the old. The surface becomes crowded with impressions, yet deeper impressions still show through at the edges. The analogy matters because it captures preservation by absence of erasing processes. It also captures overlap as a natural form of chronology. Older marks are cut by newer marks. A new visual anchor focuses on crater counts in a single region. The ground is peppered with tiny pits. Some pits sit on top of larger rims. Some pits are partly filled their bowls, softened by regolith creep. The density of pits is higher on ancient terrain and lower on younger terrain. This difference is a quiet measure of age. It does not require a single dramatic marker. It relies on statistics over area. A payoff arrives in why the moon is so valuable as a recorder. Earth is active. Its surface is recycled by tectonics, erosion, and burial. The moon lacks strong recycling. Its surface changes mainly by impact and slow weathering. This makes the moon a reference library for early bombardment. It provides context for how often big impacts happen in the young solar system. That context loops back to the giant impact story itself. The same environment that forms the moon also continues to strike it. A limit of observation is needed and specific. Crater counting is not a perfect clock. It depends on knowing the impact rate over time. That rate changes. It also depends on distinguishing primary craters from secondary craters made by ejecta. Secondary craters can confuse counts by adding many small pits after one large impact. Space weathering can also blur boundaries and make some craters hard to identify. The limit is calibration and resolution. Ages are often estimated within ranges rather than exact years. Even with that boundary, the relative ordering remains strong. More craters generally mean older terrain. Sharper rims and brighter rays generally mean younger features. The section returns to a final physical detail. A fresh crater has a crisp rim and a steep inner wall. An old crater has a rounded rim and a floor partly filled by regolith. The transition from crisp to soft is gradual. It is the moon's slow handwriting. The closing transition stays gentle. The next section follows how later lavas fill some basins and create dark plains. It explores what those plains reveal about the moon's cooling interior and its last major episodes of volcanic flow. Dark lunar plains look like calm ponds, yet they are frozen floods of rock. The early anchor is that mere volcanism fills ancient basins with basaltic lava, revealing late interior heat and pathways opened by impacts. 2 to 3 concepts guide the section. Basalt is a dark volcanic rock formed from partial melting of the mantle. Partial melting is when only a fraction melts and rises. Lava flooding is the spreading of melt into low basins that smooths the surface. At this distance, a wide basin lies under a low sun. Its rim is bright and rugged. Inside, the floor is darker and smoother. The boundary between rim and floor is not a neat line. It is scalloped with bays and peninsulas where lava meets older debris. The first visual anchor is a slow view of a lava front. A dark sheet advances across uneven ground. It thickens in low spots and thins over ridges. Along the edge, the surface skin wrinkles into low ridges and lobes. Behind the edge, the lava cools into a smoother plane with faint curved flow lines. Those lines are physical texture. They mark direction, and cooling not decoration. A first payoff arrives in why lava prefers basins. Basins are low. They are fractures in the crust and weak zones created by impacts. Melt rising from depth finds these weaknesses. Once lava emerges, gravity guides it into the lowest areas. The lava fills like water would, yet it does not splash. It creeps and spreads, then stiffens. The result is a plane that buries older craters and leaves only their highest rims as ghost rings. Basalt is dark volcanic rock from mantle melt. It is like cooled syrup that turns to stone. It is also like candle wax that hardens into a smooth sheet. It matters because basalt carries information about the mantle source and the moon's remaining heat. Basaltic plains are younger than many surrounding highlands. Their smoother surfaces and lower crater densities show that they form after the largest basins already exist. The next visual anchor moves closer to the surface of a mare. The ground is not perfectly flat. It is gently undulating. There are low ridges that run in long arcs. There are sinuous channels that cut shallow grooves. These channels look like dried rivers, yet there is no flowing water. They are lava paths. Their edges are raised in places where cooling makes natural levees. The second payoff arrives in what the channels imply. Lava is not always a broad blanket. Sometimes it is guided. A channel means flow persists long enough to carve or build a path. It also means the lava remains hot and low in viscosity for a time. The presence of channels supports the idea that eruptions can be sustained rather than instantaneous. That sustained flow changes how much of a basin can be filled. It also changes how quickly the surface can be smoothed. The story turns inward to partial melting. Partial melting does not melt an entire region evenly. It melts the components that melt most easily first. The melt collects and rises because it is buoyant compared to surrounding solid rock. It rises through cracks and porous zones. In that region, the moon's mantle is cooling over time, yet it can still contain pockets of warmth. Some warmth comes from residual formation heat. Some comes from slow radioactive decay in trace elements concentrated in certain layers. The scale shift arrives gently. A melt pocket can form at the scale of kilometers. A flow can spread across hundreds of kilometers. Over tens of millions of years, many flows can overlap and build thick plains. Over billions of years, these plains preserve the late phase of the moon's internal activity. One number helps ground the thickness of some mare fill. In some basins, mare lava can be several kilometers thick, like stacking a few mountains of stone into a broad, shallow bowl. The comparison stays calm and simple. It conveys that the dark plains are not just a surface stain. They are a substantial layer that changes the crust structure. The next visual anchor returns to a basin edge where lava meets bright highlands. The contact is sharp in places. Dark rock laps against pale ejecta and stops. In other places, the contact is gradational. Bright fragments are mixed into the dark surface, making a mottled zone. The mottling is a physical clue to mixing and erosion by impacts after the lava cools. Small craters pepper both sides. On the dark side, many craters have dark rims and lighter interiors. On the bright side, craters have bright rims and darker interiors. This inversion is a payoff. It shows that impacts dig through layers and swap colors. A fresh crater is like a window into what lies below. A simple color contrast becomes a depth probe. An everyday analogy holds the layering without repeating earlier ones. A dark glaze poured into a shallow dish fills low spots first. Later, a sprinkle of pale powder lands unevenly on top. If a small scoop removes the top, the dark glaze appears again beneath. The analogy matters because it captures burial, later dusting, and excavation. It also keeps focus on layers as a record of sequence. A limit of observation is needed and specific. The moon's internal heat sources and melt generation cannot be measured directly across the whole body. The thickness of mare basalt is inferred from gravity and from the shapes of buried craters. Those inferences depend on models of density and on assumptions about crustal structure. Some mare regions have been modified by later impacts that fracture and uplift. The visible surface is not a perfect map of what is below. The limit is that multiple interior models can fit the same surface observations within uncertainty. Even with that boundary, the broad story remains stable. Basins form first. They create low places and fractured crust. Later, basaltic lava rises and fills those lows. The filling smooths surfaces and preserves a later chapter of the moon's cooling. A payoff arrives in the timing relationship between tides cooling and volcanism. Early tides and internal warmth can keep the interior more flexible. As the moon recedes and cools, volcanism declines. Mare plains represent a late but significant release of melt. They are a fading echo of an earlier molten beginning. The section returns to a final physical detail of flow. Cooling lava forms a crust on top while the interior still moves. The top crust wrinkles into ridges. The ridges can align with flow direction or with basin stresses. In places, the surface breaks and reveals a darker interior beneath the weathered skin. The break is narrow. It casts a thin shadow line that sharpens at sunrise and fades at noon. The closing transition stays soft. The next section widens the view again. It follows how the moon's presence influences Earth's long rhythms and stability, and how that influence traces back to the same impact that creates the moon. A companion in orbit can shape a planet's long rhythm without touching its surface. The early anchor is that lunar tides steadily drain Earth's rotation and stir its oceans, creating persistent cycles that change with distance. 2 to 3 concepts guide the section. Tides are global shape changes driven by gravity. Dissipation is the conversion of mechanical motion into heat through friction. Resonance is a repeating alignment that can amplify certain motions when timing matches. At this distance, Earth is seen as a sphere with 2 broad tidal bulges. The bulges are low and wide. Their crests form smooth arcs across the oceans. Between crest and trough, a gentle gradient in height stretches for thousands of kilometers. The first visual anchor is a night-side view with a faint rim of reflected light. The bulges create subtle differences in the planet's silhouette. The silhouette is not perfectly round. It is slightly elongated along the Earth-to-Moon line. The elongation is small, yet it is real shape. A first payoff arrives in how this shape becomes motion. Earth rotates beneath the moon. Water and rock try to follow the gravitational pull. They lag because motion has inertia, and because friction resists flow. The lag turns a purely radial pull into a twist. The twist transfers angular momentum. Earth's spin slows. The moon's orbit gains energy and expands. The same process creates heat within Earth's moving water and flexing crust. Dissipation is the quiet sink. It turns organized motion into small-scale turbulence and warmth. The scene shifts to the oceans as a textured surface. Long swells rise and fall. Their crests are not sharp. They are broad ridges that travel around the globe. Along coastlines, the swells compress and steepen. The water piles slightly against boundaries and then retreats. The boundary is physical. It is the meeting of moving water with a fixed shoreline and shallow sea floor. Here the second payoff arrives. Most tidal energy is not lost in deep open ocean. It is lost where water is forced through narrow passages and over rough bottoms. Friction is strongest there. The energy becomes heat and mixing. Over time, this helps stir the ocean and distribute properties that would otherwise remain layered. The moon does not need to touch the water. Its pull and Earth's response do the work. An everyday analogy holds the idea without repeating earlier ones. A spoon is dragged slowly through thick honey. The honey forms a broad mound ahead of the spoon and a trough behind it. The mound does not keep up perfectly. It lags and shears. That shear warms the honey slightly and slows the spoon's motion. The analogy matters because it captures lag friction and energy loss in a calm way. It also avoids any need for sharp impacts or sudden events. The next visual anchor widens to Earth and Moon together. The Moon circles with a steady cadence. Earth turns beneath. The tidal bulges attempt to align with the Moon, yet they are offset. The offset is visible as a slight angle between bulge crest and the Earth to Moon line. That angle is the physical source of torque. The crest is pulled forward or backward depending on rotation rate. The Moon is pulled forward in its orbit when Earth spins faster than the orbital motion. Over time, the orbit grows. A third payoff arrives as a calm explanation of why tides change with time. Tides are stronger when the Moon is closer. The pull varies more strongly across Earth's diameter then. As the Moon recedes, the variation weakens. The bulges become smaller. The torque decreases. The rate of slowing and recession changes. The system has a built-in taper. Early on, tides can be vigorous. Later, they become more moderate. The change is gradual, not abrupt. It is a long slope rather than a cliff. One number helps anchor the pace of change without turning into a schedule. The Moon's distance increases by a few centimeters per year today, like the slow growth of a fingernail. The comparison keeps the change tangible. It also highlights the scale shift. A fingernail pace seems trivial. Over millions of years, it becomes many kilometers. Over billions of years, it becomes the vast modern separation. The scale shift deepens. A wave rises and falls in hours. A coastline experiences cycles daily. Over centuries, coastlines and basins adjust in response to repeated forcing. Over geological time, Earth's day length changes and the Moon's orbit evolves. The same basic physics operates across all scales. The details change with continents and ocean depth, yet the direction remains. The next visual anchor focuses on the ocean interior. Beneath the surface, internal waves form along density boundaries. These waves are not seen from above easily. They travel slowly along layers where water density changes with depth. When tides force water over undersea ridges, these internal waves grow and break. Their breaking mixes deep and shallow layers. A payoff arrives in how tides can influence climate scale mixing without any visible drama. Mixing distributes heat and dissolved substances. It also helps maintain circulation patterns. The lunar pull is not the only driver, yet it is a persistent driver that never stops. The Moon's contribution is steady. It provides a baseline rhythm that interacts with wind's currents and Earth's own rotation. Resonance enters gently as a concept of timing, not as spectacle. When a basin's natural slosh period matches tidal forcing tides can be amplified locally. This amplification is limited by friction and geometry. It does not grow without bound, yet it can concentrate energy into particular regions. Over time, this can shape where dissipation is strongest. It can also shape how tidal ranges vary across the globe. A limit of observation is needed and specific. Past tidal strengths are hard to reconstruct precisely because ocean basins change and continents move. The dissipation rate depends on seafloor shape and shoreline geometry which evolve. Geological indicators of past day length and tides exist, yet they are incomplete and local. The limit is that no single record captures global tidal dissipation through deep time. Models can explore plausible histories, but multiple histories can fit the present system. Even with this uncertainty, the broad mechanism remains robust. Tides transfer energy from Earth's spin to the Moon's orbit. Dissipation turns motion into heat, and mixing. The strength of tides changes as distance changes and as Earth's surface geometry changes. The section returns to a calm physical detail. The tidal bulge is smooth and broad, not a sharp hump. Its crest is slightly offset. That offset persists because nothing is perfectly frictionless. The offset is the quiet lever arm of the whole system. The closing transition stays soft. The next section widens perspective to stability and long-term consequences. It follows how a moon can influence Earth's axial behavior and long cycles, and how those cycles trace back to the same origin story. A planet's tilt can wander slowly, yet a companion can make that wandering calmer. The early anchor is that the moon's gravity helps stabilize Earth's axial behavior over long time by shaping how the spinning planet responds to external torques. 2 to 3 concepts guide the section. Axial tilt is the angle between spin axis and orbital plane. Precession is the slow wobble of a spinning axis. Torque is a twisting force that changes rotation. At this distance, Earth is seen as a spinning sphere with an axis that is not upright. The axis points in a steady direction for a while, then traces a slow circle in space. That slow circle is precession. The physical detail is a cone shape traced by the axis tip like a faint invisible funnel drawn over time. The first visual anchor is a wide view of Earth with a faint ring of light at its limb. The spin axis is marked by the direction of rotation. Around Earth, the Moon orbits in a plane that is tilted slightly relative to Earth's equator. The Moon's pull creates a gentle torque on Earth's equatorial bulge. The bulge exists because a spinning body is slightly wider at the equator. That wider equator is a physical boundary in shape. It is subtle, yet it gives the torque something to grip. A first payoff arrives in how a bulge turns gravity into a wobble. Without an equatorial bulge, a torque would act differently. With a bulge, the Sun and Moon pull on that extra mass and try to align it. Earth does not tip over quickly. Instead, the axis responds like a spinning top. The axis precesses. The direction of the tilt changes slowly, while the amount of tilt can also vary under complex influences. The Moon adds a strong and steady contribution to the torque field around Earth. This changes the characteristic rates of precession. It can make some variations less extreme by shifting the system away from certain resonant states. The next visual anchor slows down to the bulge itself. The equator is a broad band where Earth's radius is slightly larger than at the poles. Along this band, gravity and inertia balance to create a gentle outward shape. The band is not a ridge, it is a smooth swelling. The Moon's pull is stronger on the nearer side. That difference creates a twist that acts on the bulge. The twist is not constant in direction. It changes as Earth spins and as the Moon orbits, yet it has a steady long-term effect that shapes the precession rate. A second payoff arrives in the meaning of stability. Stability here does not mean a fixed tilt forever. It means the tilt is less likely to wander into extreme values. The Moon's presence changes how Earth's spin axis couples to gravitational influences from the rest of the system. It increases the precession rate of the spin axis. That faster precession can reduce the chance of strong resonance with other slow cycles. Resonance is a repeating timing match that can amplify motion. It is like pushing a swing at the right moment. It is also like a glass humming when a note matches its natural tone. It matters because resonance can magnify tilt variations if timing aligns. By changing the timing, the Moon can shift Earth away from the most amplifying matches. The scale shift is gentle and wide. A torque acts instant by instant. Precession unfolds over thousands of years. Tilt variations can develop over tens of thousands to millions of years. The Moon's stabilizing influence persists over billions of years as the orbit evolves. One number helps anchor the slow wobble. Earth's axial precession takes about 26,000 years, like a slow hand of a clock, making a full sweep on a timescale longer than recorded history. The comparison is calm and grounded. It shows that precession is neither daily nor geologic in pace. It sits in between, shaping long cycles without being felt in a single season. The next visual anchor draws that precession into a scene. A faint circle is traced in the sky by the axis direction over many millennia. The circle is smooth and it repeats. Around it, the stars are fixed in the background. The circle does not create light. It is a path in orientation. Over the same time, the Moon's orbit plane also shifts gradually. It has its own slow nodding and turning. Together, these motions create a layered pattern of cycles. A payoff arrives in why a companion can matter even as it recedes. The Moon's torque strength decreases with distance, yet the Moon also remains a significant nearby mass compared to other influences. The effect is not switched off. It evolves. In earlier times, when the Moon is closer, the torque is stronger and dissipation is larger. Over time, Earth's spin slows and the Moon moves outward. The precession rate changes gradually. The system stays coupled, yet the details drift. A limit of observation is needed and specific. The long-term history of Earth's tilt cannot be measured directly across billions of years. Evidence is indirect and often filtered through complex climate and geology. Models of tilt evolution must assume past Earth rotation rates and past lunar distances. Those are reconstructed with uncertainty. The stability claim depends on how resonance zones are modeled and on how dissipation changes with ocean basins and continents. The limit is not that the physics is unknown. The limit is that initial conditions and past dissipation are not perfectly constrained. Even with that boundary, a broad conclusion remains reasonable. A large nearby moon changes Earth's spin dynamics in a stabilizing direction by altering precession and resonance behavior. This links the Moon's origin to Earth's long-term rotational character. The section returns to a physical detail that keeps the story tangible. The equatorial bulge is a smooth swelling. Torque acts on that swelling, precession is the response. This chain is simple in outline even when details are complex. An everyday analogy carries the chain without repeating earlier ones. A spinning plate balanced on a pin does not fall at once when nudged. It traces a slow circle instead. A second weight attached nearby can change how quickly that circle is traced. The analogy matters because it captures precession as a response to torque rather than as a separate mystery. A final payoff arrives as perspective. The Moon begins as debris from a collision. Over time, it becomes a stabilizing partner in a gravitational dance. The same event that shapes lunar chemistry also shapes Earth's long rhythms through tides and torques. The closing transition stays soft. The next section evaluates alternatives again. It compares how different origin scenarios struggle to satisfy orbit composition and dynamics at once without opening new mysteries. An origin idea becomes convincing when it survives several different kinds of tests at once. The early anchor is that capture and co-formation struggle to match orbit composition and energy together, while a giant impact fits more constraints in one frame. 2 to 3 concepts guide the section. Angular momentum is the shared budget of spin and orbit. Capture is acquiring a passing body into orbit by losing energy. Co-formation is building 2 bodies from the same local disk around the Sun without a major collision. At this distance, Earth and Moon appear as 2 spheres linked by gravity. The Moon's orbit is nearly circular and lies close to Earth's equatorial plane compared to a random incoming body. That geometry is a physical detail. It is a smooth loop with a stable plane, not a wildly tilted path. The first visual anchor is a slow diagram made of light and shadow in space. A faint ellipse circles Earth. The ellipse is thin and even. Along it, the Moon passes with steady speed. Around Earth, a second faint ring marks the equatorial bulge that tides act on. The two rings are nearly aligned. This alignment is one of the quiet checks any origin story must explain. A first payoff arrives by asking what capture requires in physics terms. A passing body is on an open path. To become a satellite, it must lose enough energy to become bound. In space, there is no air to provide drag at the required scale. A three-body interaction can exchange energy, yet it often produces a distant or highly elongated orbit. The captured body would also likely arrive with a composition not closely tied to Earth's mantle. Capture is possible in principle, yet it requires conditions that are hard to arrange while also matching chemistry in the current orbit. A second payoff arrives with the co-formation idea and its quiet tension. Co-formation suggests Earth and Moon grow side by side from the same local population of solids. This can naturally produce some compositional similarity, yet it struggles with ion content and with the specific angular momentum of the Earth-Moon system. If both bodies grow from the same region, the Moon might be expected to share more of Earth's ion fraction than it does. It also does not automatically explain a large satellite relative to the planet. Many co-forming systems create multiple small moons or none at all depending on disk conditions. The Moon's mass compared to Earth is unusually large for a terrestrial planet satellite. The next visual anchor shifts to a calm pile of constraints seen as three stones that must balance on one another. One stone is composition, another is angular momentum, another is thermal history. The stones do not stay balanced easily under capture or co-formation without extra adjustments. The third payoff arrives when the giant impact is placed under the same stack. A glancing collision can supply angular momentum in the right range. It can preferentially loft mantle material and leave much of the iron in Earth. It can also create a hot disk that enables mixing, which helps explain isotopic similarity. It naturally produces a satellite forming from orbiting debris rather than from a pre-existing body arriving fully formed. This is not a claim of perfection. It is a claim of fit across multiple dimensions. An everyday analogy holds the multi-constraint nature of the problem without repeating earlier ones. A key must match several cuts at once to turn a lock. A key that matches only one cut fails even if it looks close. A key that matches most cuts can turn with minor friction. The analogy matters because it frames the origin as a constraint satisfaction problem rather than a single dramatic story. It also keeps tone calm and methodical. One number helps anchor the angular momentum scale without heavy notation. The Earth-Moon system carries a large share of its total angular momentum in the Moon's orbit, like most of a spinning carousel's motion, stored in the outer rim rather than the center. This comparison avoids formulas and keeps the point tangible. Any origin story must create this distribution. Capture tends to produce an initially elongated orbit that must circularize, which requires long-term dissipation. Co-formation must create a separate body with the right orbit while the planet is still growing. The giant impact creates a debris disk already in orbit and already linked to Earth's rotation, which makes the accounting more natural. The scale shift is gentle. The differences begin at the atomic scale in isotope ratios. They expand to global scale in ion content and volatile depletion. They extend to orbital scale in distance and plane alignment. They persist over billions of years as tides reshape the orbit. A single origin must seed all of these. That is why the evaluation uses many scales at once. The next visual anchor returns to the aftermath disk. A wide ring circles Earth. Inside the ring, clumps cannot survive. Outside, clumps gather. The ring has a sharp inner boundary and a softer outer edge. Above it, a thin vapor veil fades into space. This image is a direct product of an impact scenario. It is also a mechanism that can produce both mixing and loss of volatiles. Capture and co-formation do not naturally generate this particular intermediate stage. They would need added processes to mimic it. A payoff arrives in the meaning of this intermediate stage. A debris disk acts as a processing chamber. It is hot enough to allow exchange. It is open enough to allow some escape. It is structured enough to allow accretion into one body. This combination is rare in other scenarios. The disk links chemistry, heat, and orbit in one step. This is why the giant impact is often favored. It does not solve every detail, yet it provides a single bridge across several domains. A limit of observation is important here and specific. The impact itself is not observed. The exact impactor properties are not known. Multiple impact scenarios can reproduce similar end states with different initial spins and angles. Some isotope systems show subtle differences that require careful interpretation. Models of the disk depend on assumptions about vapor behavior, droplet sizes, and mixing efficiency. The limit is not a lack of physical laws. The limit is uncertainty in initial conditions and in how well simulations capture complex material behavior. This is why debates persist about details such as how much of the moon comes from Earth versus the impactor. Even with this boundary, the general conclusion remains resilient. A large glancing impact best satisfies the combined constraints of mass orbit composition and thermal processing. The section returns to a calm summary in physical terms. Capture needs a strong energy loss pathway that is not easily supplied. Co-formation needs a natural route to an unusually large moon with unusual iron and volatile patterns. The impact provides both a source of orbiting mantle-rich material and a processing disk that can mix and fractionate. The closing transition stays gentle. The next section turns toward resolution and rest. It gathers the story into a single long perspective where one early collision shapes billions of years of chemistry, orbits surface record and planetary rhythm. A pale moon can seem like a simple companion, yet it is a long echo of one early collision. The early anchor is that a giant impact sets the moon's material, its orbit and Earth's long rhythms in one connected chain. 2 to 3 concepts guide the closing. Constraint matching is the way multiple clues converge on one scenario. Continuity is the persistence of early conditions into later history. Perspective is the ability to hold many scales at once without forcing precision where it is not earned. At this distance, Earth and Moon hang in darkness with a quiet separation. The Moon's orbit is a smooth loop. Earth's limb shows a thin gradient from day to night. Between them, gravity is not visible, yet its effects are written in shape and motion. The first visual anchor is a slow view of the Moon above Earth's horizon. The Moon's edge is sharp. The bright half fades into a soft terminator line that curves like a calm arc. Along the terminator crater rims cast thin shadows. The shadows make the surface look textured and old. A first payoff arrives by gathering the chain into one plain idea. A glancing impact lofts mantle rock into orbit. That orbiting rock forms a disk. The disk mixes, cools, and accretes into a moon. The moon begins hot. It forms a magma ocean. It sorts into layers. It loses some volatiles because the disk is open at its edges. It keeps many isotopic similarities because mixing is strong while everything is hot. Each part supports the next without needing extra inventions. The next visual anchor returns to the disk as a memory rather than a present object. A faint ring appears around a glowing Earth. The ring has a sharper inner edge and a softer outer fade. Above it, a thin veil of vapor lifts and then thins into space. Within the ring, clumps are torn apart. Beyond it, clumps survive and grow. The ring is like a boundary drawn by tides. The ring is also like a reservoir that slowly empties into one growing body. A second payoff arrives in why the Moon is not only a result. It is a tool for reading the early solar system. Its craters keep a long record. Its basalt plains show late interior heat. Its crustal layering shows early flotation and sorting. Its chemistry shows both mixing and selective loss. These are not separate stories. They are chapters of one formation sequence. The Moon becomes a reference for processes that are hard to preserve on Earth, where surfaces are recycled and erased. An everyday analogy holds the whole arc without repeating earlier ones. A drop of ink falls into clear water and spreads. At first, it is concentrated. Then it forms wisps and gradients. After enough time, the water looks uniformly tinted, yet faint streaks can still hint at the path the ink took. The analogy matters because it captures a single event, leaving both a blended outcome and subtle preserved traces. It also captures how mixing can be strong without making everything identical. One number anchors the vast timescale that the Moon connects. The impact and assembly occur about 4.5 billion years ago, like placing the first stone at the start of a long bridge that still reaches the present. The comparison is gentle. It keeps the scale from feeling abstract. It shows that the Moon is not a recent addition. It is part of Earth's earliest architecture. The scale shift is calm and wide. The story begins at the atomic scale with isotope ratios. It moves to droplet scale in a hot debris disk. It grows to a moon-sized body with a magma ocean. It extends to orbital scale as tides transfer energy. It continues over billions of years as craters accumulate and lavas flood basins. It ends in a present sky where the same face looks back because tidal locking has done its slow work. The next visual anchor settles on a quiet mare plain. The surface is dark and smooth compared to surrounding highlands. Small craters pepper it. Their rims are low. Their shadows are soft. In places, faint wrinkle ridges curve across the plain like low waves frozen in stone. The ridges are physical evidence of cooling and contraction. They show that even late lava plains continue to adjust as the interior cools. A payoff arrives in how orbit and geology speak to each other. As the Moon recedes, tidal heating in the Moon diminishes. As the Moon cools, volcanism fades. As impacts continue, the surface becomes more regolith and less sharp. Meanwhile, tides on Earth continue to dissipate energy and slow rotation. The same gravitational link influences both bodies. It changes their motion and their internal states, though, at different strengths and in different ways. A limit of observation belongs even in this closing, and it is specific. No sample captures the entire Moon. No model captures every detail of impact physics and molten behavior. Some measurements are sparse, and some interpretations compete. The exact fraction of Moon material that comes from Earth versus the impactor remains uncertain in detail. The thickness and lifetime of the post-impact vapor veil are not observed directly. These limits set boundaries on confidence in the fine print. They do not erase the broad coherence of the impact framework across many constraints. Constraint matching remains the quiet strength. The Moon's size, orbit ion content volatile pattern, and many isotope similarities align more naturally under a giant impact than under capture or simple coformation. Continuity then carries the story forward. The early disk sets initial chemistry and heat. Early tides set the direction of orbital evolution. Early cooling sets crust and mantle structure. Later impacts and lavas modify the surface without rewriting the origin. The closing visual anchor returns to the Earth-Moon pair as a stable system. Earth's tidal bulges are small yet persistent. The Moon's orbit is steady. The terminator line crawls across the lunar face with a slow grace. The surface texture remains crater by crater, as if time itself has been stored in shadow. The end turns gently toward rest without opening new questions. The Moon remains in its path and Earth remains in its spin, both shaped by a single ancient reshaping event. The long chain settles into a quiet orbit that continues without strain,